Okay, good morning, lads and ladies. Welcome back to Calc 2. Today, we are going to be playing around more with some series. Your study guide is up. I do apologize. I meant to have that up on Wednesday for you, but it is up, and I invite you to work on it. I put 20 problems in there, which are problems that will help you get more comfortable with all of the tests for series. There's also a couple improper integrals and a couple sequence problems in there, so it's representative of all the material that could show up on the test. I want to remind you that probably the most important thing you can do as you're studying for this, as you're solving those problems, is to make sure you're writing your answers in complete sentences and sharing them with other people. More than anything else, you really need to check that your logic is sound. And the way you check that that logic is sound is by writing out the logic that you're using. You can read it back to yourself and ask, does this make sense? But in the same way that it's kind of hard to notice flaws about yourself, it's kind of difficult to notice if you've made a mistake in your logic, if you're the one checking it. So I want to really implore you guys to share your solutions with each other, share them with me, share them with tutors at the Learning Commons or anybody you know who has done well in this portion of this course. I know people like that are hard to find, but I promise you they're out there. So please use each other as a resource, use me as a resource, and check if your logic is correct. It can be very tempting to just go through and click converge or diverge until you get them right, move on and call it a day. But that's not going to do the thing, right? What we need to do here is make sure we're understanding the logic and writing out full, correct, complete arguments. So yeah, please do that because that's what you'll be graded on in the test. Another quick reminder, in order to get credit for the study guide, you need to submit the written work for those problems. So let me go ahead and turn on the screen share here and just remind you briefly how this works. So as you solve the study guide problems in WebAssign, show you here really quickly what your study guide looks like. Here's the study guide. It's due next Wednesday. The test is next Wednesday. As you solve these 20 problems, make sure you are writing out your solutions. And that written work for those solutions, you need to submit to the assignment here in Canvas, Study Guide 2. And over the next week or so, I will be going in and looking to see as people submit. I'll try my best to get in there and make written comments on them, say, here, this solution isn't quite right, or this looks perfect, or make sure you add this sentence here, things like that. So yeah, in order to get credit for the study guide, you got to submit the problems. You got to scan that work and submit it here. It's not sufficient to just just to put the answers in WebAssign. Yeah, Kim, thank you for asking. So the test is next Wednesday. That's correct. If you want to take the test at the testing center, you do not need to ask for a reservation this time. So because of the way the testing center has changed their procedures, I'm going to be making a blanket reservation for you guys. And it's not going to, you don't have to take the test right at 9:30. You can come in anytime after 9:30 next Wednesday and sit down and take the test. The catch is they might not have a proctor there to work with you at the moment you come in. So you may have to wait for a proctor to become available or for a computer to become available. So you don't need to make a reservation. If you want to take the test at the testing center, you just show up there. That's fine. You don't need to email me or anything like that. You do need to make sure that you have the time in your day to potentially sit there for a little while a computer becomes available. But that's it. You just show up there at 9:30, and as soon as computer and proctor are available, they will sit you down and you will take the test. Okay, let's get some of this stuff in writing. It's a beautiful day outside today. It's a little cloudy, but nice to have this change in the weather. So this is MAC 2312, section 004, which means we're talking about Calc 2. Today is the 29th of October, 2021. And some announcements. First, the date. Exam 2 is next Wednesday. Which is the 3rd of November. You can take it online with me. This means you use Zoom on your phone and Honor Lock on your computer. Or you can take it at the testing center. Anytime after 9:30 on that day. And you don't need to make a reservation. Basically, it's, I think I explained this last time. If I tried to make a reservation, an individual reservation for everybody who wanted to take the test there at 9:30, they don't have enough people to proctor, right? So if we got like 10 people that want to go there and take the test at 9:30, I think they probably only have like 2 or 3 proctors working at any given moment. So instead of that, what we can do is just tell them it's going to be an all-day walk-in testing situation where you guys just show up whenever you want after 9:30, and they will get you down on a computer with a proctor working on the test as soon as they can. But it could be a while. You might have to sit there and wait. But there's no need to email or reserve a spot. I will make a blanket reservation for the whole class. What else? The study guide. Remember, you need to scan and upload the work for those problems. So getting credit for the study guide, that doesn't come from solving the questions in WebAssign. It does not come from completing the assignment in WebAssign. Those 25 points for each study guide come from scanning and uploading your work for those problems in Canvas. And the idea there is that I can take a look at your written work and give you some feedback. At the testing center, anytime after 9:30. Anytime after 9:30. Does not have to be between 9:30 and 11. If you're going to take the test online with me, this has to be during class time, right? I will be posting a link, just like our normal classroom meeting link, and you would have to come and take the test right then at 9:30. But if you're going to take it at the testing center, you can show up there anytime after 9:30 a.m. and you'll be good. Obviously, you have to go there during their hours while they're open. So like, don't show up at 10 p.m. going, hey, I'm here to take the test. But you know, within reason. I think they close at like 8 or something. N216, Monday through Thursday, 8 to 8. So next Wednesday, if you show up there even at like 5 p.m., 6 p.m., you're fine. Of course, the test covers everything from 7.8 through 11.7. 11.7 is kind of what we're talking about today. It's not anything new. It's just an amalgamation of problems from earlier in chapter 11. Very good, very good. Any other questions, procedural questions about the test, stuff like that? If you do take the test online with me, I'm going to ask that you keep Zoom on your phone, stay in the Zoom meeting while you scan and upload the written work. There have been some problems where people think they've submitted the written work after scanning it, but it hasn't gone through because Canvas sometimes doesn't like to take submissions from phones. So I'll ask that you stay in that Zoom meeting until I can confirm that I've gotten your written work. That's pretty important. If you're taking the test at the testing center, then you'll just give them your written work after you finish. I think it's kind of easy to forget if you're taking the test at the testing center that you need to show all of your work on that paper. It's still graded the same way as whether you take it online. So I'm going to look at your written work and your typed answers. The typed answers are just there to confirm the written work, right? So make sure you type your final answer in the box. That's how I verify that the work you did on the paper you did during the test. And then what I grade is the work. The number of questions on the test, same distribution as last time. So there's going to be 4 true false, 4 multiple choice, 6 free response, and they're each worth 4 points for the true false, 6 points for each multiple choice, and 10 points for each free response question. Sections on the test, let's go ahead and write it down. 7.8, which is improper integrals. 11.1, which is sequences. 11.2, which is intro to series. That 11.2 section has the definition of an infinite series, partial sums, geometric series, telescoping series. Oh, and also the test for divergence. Then 11.3, which is on the integral test. 11.4, which is on the comparison tests. There's 2 of them. Those are the direct comparison test and the limit comparison test. 11.5, which is the alternating series test. 11.6, which is on absolute convergence. I'll say absolute versus conditional convergence. And the root test and ratio tests, so I'll say RTs, root and ratio tests. And then 11.7, which is strategies for testing series. So 11.7 is a lot like 7.5. Remember section 7.5 before exam 1, which is on strategies for integration. 11.7 is strategies for testing series. So if you look at a series, how do you know what test to use? What order should you try things in? That's what we're going to talk about today. So it doesn't actually contain any new theorems or any new tests or any new results. It's just a section that's in there to help you kind of put together all the material from the previous 5 sections. Richard asks, do we have to type out the argument in your box? No. So in the box on the test, you'll just type your final answer. So for example, a problem might ask, determine whether the series converges absolutely, converges conditionally, or diverges. And in the box, you would just type series converges absolutely. And then on your paper, you would have all the work. I might include something like a little more specific. I might say, tell me what test you used. So you might say the series converges absolutely by the ratio test in the box. And then on your paper, you would show me all the work for the ratio test. But the instructions on each question will be very clear. And so again, the typed answer in the box is really just there so I can verify that the written work is what you did during the test. In the past, it has been the case that people left those boxes blank and then tried to sneak in some extra work on the paper after the test was done before uploading. So I need your typed answer in the box just to verify the stuff that's on the page. That's really the reason for that. Okay. Any other questions about the test, procedure stuff, anything like that? Happy to be fully transparent. Anything you want to know besides what's on the test. Okay. So I'd like to take a look at section 11.7 with you. I don't want to write all of these things down, but you may want to write some of them down. I'll give you like a Reader's Digest version of this. But again, this is just trying to help you figure out what tests to use and in what order. So if I hand you a series, what should you ask yourself? What should you try first? Those sort of things. Now, here's what the book says. If I hand you a series, then you should first ask yourself, is the thing a p-series? Does it look like sigma 1 over n to the p? If it is a p-series, we know everything about them. It'll converge if p is bigger than 1, and the series will diverge if p is less than or equal to 1. If the series is not a p-series, you should ask yourself, is this thing geometric? Is this a geometric series? Does it look like, some sigma, then some constant times some number to the n, or n minus 1? Is it a geometric series? Again, we know everything about geometric series. So if it is a geometric series, then you ask yourself, what's the common ratio? And what's the absolute value of the common ratio? If the absolute value of the common ratio is less than 1, then your series converges. And if the absolute value of your common ratio is anything else, then the series will diverge. And you might want to do some algebra. It might not immediately be obvious that the series is in either of these forms. You might have to play with the algebra just a little bit, and you've seen that in your homework. If your series is not a p-series and it's not a geometric series, the book suggests you check to see if it's similar to a p-series or a geometric series. Right? Is it like almost a p-series, but it's got a +1 downstairs or something else like that, or it's almost a geometric series, but it can't quite be put into this form because there's some other term either in the numerator or denominator. If your series looks very similar, and remember that's the kind of like intuitive thing we were doing where we ask, what are the dominant terms upstairs and downstairs? If the series is very similar to a p-series or a geometric series, then you should try to compare to that similar p-series or geometric series. They say in particular, if an is a rational or algebraic function of n, then probably you can compare to a p-series. Which comparison test you use, the limit comparison test or the direct comparison test, depends on whether you can build a nice inequality for the direct comparison test or not. If that inequality doesn't jump out at you reasonably fast, then you should probably try the limit comparison test. If you do see a nice inequality, if you think your series is smaller than a convergent p-series, then you should try to show that inequality. There is a note here that is very important. Comparison tests only apply to series with positive terms. So if your series does not have exclusively positive terms, you cannot use a comparison test. However, sometimes it's very smart to look at the absolute value series instead, and then apply the comparison test to that. Remember, if sigma absolute value an converges, then sigma an itself must converge. And this thing is guaranteed to have positive terms. So if your series looks similar to a p-series or geometric series, but does not have exclusively positive terms, take absolute values inside and then try a comparison test with that. The book then says, try the test for divergence. I would say this is what you should do first. Before you do anything else, ask yourself, do the ANs go to 0? If yes, then fuck it, move on, not worth doing. If no, or if it's not obvious, then you should run the test for divergence. If your series gets through all of these things and you still don't know what to do, ask yourself, is this an alternating series? If it's an alternating series, then you could try the alternating series test. Might not be the best move, but it is an option. If your series has any factorials or factorial-like products, then you should consider the ratio test. In fact, I would go as far as saying if you got a factorial or factorial-like product, you should do the ratio test immediately. You shouldn't do anything else. And they say, be mindful that the ratio test fails on p-series and anything like a p-series. So anything that you could compare readily to a p-series or p-series themselves, the ratio test is totally useless on, will not work. If the terms of your series are a bunch of shit raised to the n, right? If this bunch of shit is constant, then it's a geometric series. You need to go back and do it like that. But if you've got a bunch of non-constant shit raised to the n, that's a really good candidate for the root test, because you're going to take the nth root and that will kill that nth power. And then at the very bottom here, they say, you know, if all else fails, you don't know what to do, and you know how to integrate the associated function, the integral test might work. Remember, you need to check those three hypotheses. Is the function positive, continuous, and decreasing? The reason this is down here at the very bottom is because it's a pain in the ass, right? It takes forever to check those three things and then do an improper integral. So the integral test, while it's kind of the most intuitive, or one of the more intuitive tests we have, is sort of our last ditch thing because it just takes so long. And most of the series you're going to play with, if you could do it with the integral test, you could probably do it with something else too. Not always, though. The only modifications I would make to this, I would say test for divergence you should do in your head before starting any of this shit. Before doing any of this stuff, you should ask yourself, do the ANs go to 0? If they obviously go to 0, there's no need to write anything down. If they do not obviously go to 0, or they obviously do not go to 0, then you should write down the test for divergence, because that'll do the trick. And up here, where they talk about p-series and geometric series, I would insert telescoping series. Do you think this series might telescope? Now, here they're just talking about convergence tests. Telescoping series stuff is technically not a convergence test, but it is the correct way. You know, writing out the partial sum is the correct way to approach a telescoping series, and you should ask yourself right away, around the same time you're asking, is this a p-series or is this geometric? You should ask yourself, might this series telescope? And if you think it might, then you should try to write out the partial sum, right? Maybe do some partial fractions and write out the partial sum. Okay. One other little word about the test here. Let me come back this way. I will almost certainly ask you for examples on this test. Like, I could say, give me an example of a series that converges conditionally, or give me an example of a series, you know, an alternating series that diverges, or something like that, right? So asking you for examples of series that have certain properties is definitely something I could do, and it's definitely a question that question type that tends to show up here. Right? Give me a sequence that is bounded and divergent. Those are all questions that have appeared on this test. Bounded here, by the way, means doesn't go to infinity. That's all bounded. So stuff like that, right? It's a good way to check your understanding. I could give you the partial sums of a series. I could give you a formula for S sub capital N and ask you whether the series sigma AN converges or diverges. That would be a good question from like the 11.2 stuff. All right, I think this is enough just rambling. Let's look at some problems. I'm going to pull a few problems from 11.7 for us to work on, and I would like you guys to also let me know if there are any particular problems you want to see. So I promised that we would look at some weird factorial-like products today. In fact, let me go back to 11.6 for a couple of those. Yeah, stuff like this I said we would look at. So let's look at some stuff like this. A lot of folks do struggle with those. 21 is the first series here that has a factorial-like product in it that is not a straight-up factorial. So I'll say investigate. I'm just going to write it down and I'll switch back. Investigate series. S equals 1 minus 2 factorial over 1 times 3 plus 3 factorial over 1 times 3 times 5. Yeah, minus 4 factorial over 1 times 3 times 5 times 7 plus and so on. Few challenges here. First, the product in the downstairs is a little weird. Second, it's not given in sigma notation. So it's not immediately obvious what we should do. Or maybe it's not immediately obvious what we should do. I guess that's a matter of opinion. I think probably it's wise to rewrite this in sigma notation. Usually we want to look at a series in both forms, right? If it's given to you in sigma notation, you should write out the first few terms. If they've given you the first few terms, you should probably try writing it out in sigma notation. And I want to show you what products like this in the downstairs look like in sigma notation, because I think they're easier to understand in this notation, but sometimes they're given to you in sigma notation. You have to understand what they are. So I'll just start by saying in sigma notation, I can write S as, I'll worry about the starting value of n in a second. It's going to be probably going to be 1. But what else is going on here? Yeah, in fact, let me just go ahead and say that the series will start at 1. Well, this series is alternating, right? First term is positive, second term negative, third term positive, fourth term negative. And if we're starting at n equals 1, then to get the first term to be positive and the second term to be negative, and so on, I would use -1 to the, you could either use n plus 1 or n minus 1, but not -1 to the n. -1 to the n would start negative and then go positive and so on. Upstairs, I have straight up factorials, right? Like this numerator, I can think of as 1 factorial. So it's 1 factorial, 2 factorial, 3 factorial, 4 factorial. So upstairs is just n factorial. And there is a kind of standard notation for writing this denominator. The next term here would be 5 factorial over 1 times 3 times 5 times 7 times 9. And the term after that would be 6 factorial over 1 times 3 times 5 times 7 times 9 times 11. So what's going on downstairs is you're multiplying all the odd numbers, right? Here you've got the first 2 odd numbers. Here you've got the first 3 odd numbers. Here you've got the first 4 odd numbers. So what lives down here is the product of the first n odd numbers. What is the nth odd number? I think maybe 2n minus 1. 2n plus 1 is also like a generic odd number. But I think if you plug in like n equals 1 here, you get 3, which is the second odd number. If you plug in n equals 2 here, you get 5, which is the third odd number. So we want 2n minus 1. But downstairs here, it's not just 2n minus 1. It's the product of all the odd numbers up to 2n minus 1. And the way we write that is 1 times 3 times 5 dot 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 out to 2n minus 1. And if you see something like this in your sigma notation, you need to know that this is what it means. And I think a lot of people struggle with understanding what these products mean. So we'll practice going back and forth. And if you were to plug n equals 1 into this thing, you'd have -1 squared, which is 1, times 1 factorial, which is 1, divided by this product. And when you plug n equals 1 in here, it's not immediately obvious, but this product would be 1 times 3 times 5, all the way up to 2 times 1 minus 1, which is 1. So really that denominator, when you plug in n equals 1, is just 1. The way we interpret this is the product of the first n odd numbers. So when n is 1, that's the product of the first 1 odd numbers. Okay, that's 1. When n is 2, that's the product of the first 2 odd numbers, which is 1 times 3. When n is 3, it's the product of the first 3 odd numbers. That's 1 times 3 times 5. So there is another notation for this. I don't expect you to use it, but there's something called a multifactorial, and it doesn't mean what you would think it means. It's not the factorial of the factorial. It's the factorial-like product where you skip every 2 instead of skipping every 1. The triple factorial would be like 1 times 4 times 7 times. Don't need to worry about this. You do need to know how to interpret this thing. All right, what test should I use? Definitely the ratio test, right? Definitely the ratio test because I've got a factorial and a factorial. Oh my God, that was beautiful, baby. Thank you. I'm use the ratio test. I skip over all that other crap because I recognize that there's some factorial and factorial-like stuff here. Immediately, ratio test. Ratio test says let L be the limit as n goes to infinity, absolute value an plus 1 over an. And if this number comes out less than 1, my series converges absolutely. If this number comes out bigger than 1, my series diverges. If this number comes out to 1 itself, then I don't learn shit, which would suck. It's nice to go ahead and write that L equals lim n to infinity absolute an plus 1 over an, because then I can give you some partial credit for it, even if you mess up the next step. I'm going to embiggen things here. My an plus 1 would be -1 to the n plus 2 times n plus 1 factorial divided by this product, but with n replaced by n plus 1. So if an has downstairs product of the first n odd numbers, then what should be here is the product of the first n plus 1 odd numbers. So that product is going to end at 2n plus 1. This would be 1 times 3 times 5 up to second to last term would be 2n minus 1. And then the next term after that would be 2 times n plus 1 minus 1. So this is a sub n plus 1 right here. And then to divide by an, I'm going to multiply by the reciprocal of an. So that's 1 times 3 times 5 up to 2n minus 1 divided by -1 to the n plus 1 times n factorial. Take a second, make sure you're comfy with why this is an plus 1, specifically the downstairs. Remember, an plus 1 is the next term in the series after an. It's what you get by swapping n for n plus 1 here. So the -1 to the n plus 1 would be -1 to the n plus 1 plus 1. N factorial would become n plus 1 factorial. And that downstairs product, instead of being the product of the first n odd numbers, should be, and this is the nicest way to think of it, product of the first n plus 1 odd numbers. Right, that product downstairs grows in length by 1 every term. And you can get it just by plugging in an n plus 1, right? 2 times n plus 1 minus 1. And this is going to be 2n plus 1. But I think it's also very nice to write the term that comes before, because that will help you see the cancellation. Just like when we're writing out factorials, right? You write the first few terms and the last few terms. So let's see what we can do with this thing. This is the limit as n goes to infinity. I'm going to put all the similar looking pieces together. Negative 1 to the n plus 2 over negative 1 to the n plus 1. It's all still in absolute values. Times n plus 1 factorial over n factorial. Times the product of the first n odd numbers, 1 times 3 times 5 out to 2n minus 1, divided by the product of the first n plus 1 odd numbers, which is 1 times 3 times 5 out to 2n minus 1 times, and this is 2n plus 2 minus 1, which is 2n plus 1. Right, the n plus first odd number is 2n plus 1, like we said at the start. So now that I've kind of shuffled all the relevant pieces next to each other, we can start canceling and cleaning up wherever possible. What is this? Negative 1 to the n plus 2 divided by negative 1 to the n plus 1. Just this piece. What is that?
Negative 1 to the 1.
Very good. Yeah, it's just negative 1. Okay. N plus 1 factorial over n factorial. What is that? Maybe we should write it out. So n plus 1 factorial is n plus 1 times n minus 1, all the way down to 3 times 2 times 1. And n factorial itself is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And then over here in my odd product, I can cancel the first n terms on the top with the first n terms in the bottom. So that last chunk there is just 1 over 2n plus 1. So this is what we get there. And I can also cancel a lot in the factorials, right? I've got an n factorial upstairs here and an n factorial downstairs here. The only thing that's left is the n plus 1 from the top. So I get here limit n to infinity, absolute value of negative 1 times n plus 1 over 2n plus 1. And we can split up those absolute values. This is the absolute value of negative 1 times the absolute value of n plus 1 over 2n plus 1. And the absolute value of negative 1 is just 1. So this guy is going to go away. The absolute value of n plus 1 over 2n plus 1, n is going to positive infinity. This term is most definitely positive. So my absolute values are gone in this next step, and the -1 piece is gone. This is just n plus 1 over 2n plus 1. And we're at a stage in our mathematical adventures where you should be able to tell me what this limit is without any further work. What is this limit? Yeah, Richard has it correct in the chat. This is 1/2. You could use L'Hopital's rule, and one run of L'Hopital's rule will get you there. Or you could divide top and bottom by n, and you would get 1 plus 1 over n divided by 2 plus 1 over n. However you like to do it, renormalizing or L'Hopital's rule, or just saying at this point, I've done a million of these, so I know what this is. This is 1/2. That's fine with me. And that's the ratio test limit. Any questions on how we found this to be 1/2? You should think carefully. We only have a couple opportunities to ask questions before the test. This is a good time to do it. I'm thinking specifically about this. This is what I see people struggle with a lot. So the idea here, yeah, I'm glad you say that. So the idea here, let me some annotation off to the side here. AN is -1 to the n plus 1 times n factorial over 1 times 3 times 5 out to 2n minus 1. So think about like function notation. If I told you this was f of n, then what I'm looking for down here is f of n plus 1. And if we kind of mindlessly replace n by n plus 1, we would get -1 to the, we always do it in parentheses, n plus 1 times n plus 1 factorial divided by 1 times 3 times 5 out to 2 parentheses n plus 1 plus 1. So really all I'm doing here is taking all the n's in this statement and replacing them by parentheses n plus 1. All the n's in an get swapped for parentheses n plus 1. So this -1 to the n plus 1 becomes -1 to the parentheses n plus 1 plus 1. This n factorial becomes parentheses n plus 1 factorial. And downstairs here, if I'm not thinking super carefully, then the 1 times 3 times 5 stays 1 times 3 times 5, and 2n minus 1 becomes 2 parentheses n plus 1 plus 1. Oh, sorry, this should be a minus 1. So everywhere there's an n in an, I plug in n plus 1, and that's how I get an plus 1. And then if we think very carefully about what this denominator is, yeah. So the numerator is now -1 to the n plus 2, and then upstairs is n plus 1 factorial, and downstairs is 1 times 3 times 5 out to 2 times n plus 1 minus 1 is 2n plus 1. You could write it like this. You could write it like this. But just like when I write out any factorial, like when I write out n factorial or n plus 1 factorial, we write the first few terms and the last few terms because we know we're looking to cancel shit. When I write out a product like this, 1 times 3 times 5 up to 2n plus 1, I think it's very nice, in addition to writing the first few terms, to write more than just the last term, specifically to write the term that comes just before this. So we ask ourselves, what's the odd number directly before 2n plus 1? Well, 1 less than 2n plus 1 is 2n, and that's an even number. So the next odd number as we're going down is the number underneath 2n, which is 2n minus 1. So I think it is useful, it's nice to write this one times 3 times 5 out to 2n plus 1 as 1 times 3 times 5 2n minus 1 2n plus 1. All right, having the first few terms and the last few terms instead of just the last term does a lot for us. First, it again makes the cancellation easier because you know in your ratio test you have this piece up here. So it'll tell you exactly what cancels. Also, it just helps you understand the product a little bit better, right? So if I wanted, suppose I've written the first 3 terms here. Suppose I wanted to write the last 3 terms here. What's the term before 2n minus 1? What's the next term hiding in the dot, dot, dots as we come down here? Very good, Richard. 2n minus 3, right? So it kind of just helps us to understand what terms are in that product. Does this help? So the challenge, if you just wrote, as Jose asked in DM, can we just write this out to 2n plus 1? You can, you absolutely can. But if I just had this written like this here, 1 times 3 times 5 up to 2n plus 1, would you see that the 2n minus 1 cancels? I don't know, maybe. At the very least, you would have to kind of pause a minute and think about it, right? You'd have to ask, so from this odd product upstairs, what cancels in the denominator? And if my denominator here is just 1 times 3 times 5 dot, 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 2n plus 1, you might have to ask yourself for a minute, does the 2n minus 1 from the top cancel? The answer is it does. And it does because the term right before 2n plus 1 in the bottom is 2n minus 1. But it might not be super obvious unless you write it. So I think it is helpful to write this thing. This is an accurate description of the denominator of an plus 1, but it's helpful to write it like this because that makes it easier for us to see the cancellation. Okay, we didn't quite finish the problem, so let me try to squeeze in the last bits here. Since L is 1/2, which is less than 1, the series S does what? What's the result from the ratio test? If L comes out to 1/2, since 1/2 is less than 1, we can conclude what about the series S? Excellent, Coburn. Converges absolutely. Don't forget the absolutely. And then if I'm writing in full, correct, useful sentences, you could stop here, but it's nice to say by the ratio test. That way, if the person reading your work is unsure what you're saying, they can say, oh, the ratio test, that's right. Yeah, if L is smaller than 1, then the series converges absolutely. Okay, this is a full, beautiful solution to this problem. You give me this shit on the test, I will be a happy man as I grade and gladly write 10 out of 10. Last call for questions here. If you want to use the double factorial notation, I'm fine with that. If you want to use multifactorial notation in general, I am fine with that. You may want to read up on it a little bit. Wikipedia page is good. In mathematics, please. Yeah. All right. Yeah, I'm fine with you using double factorial or triple factorials, whatever you want. But definitely make sure you understand what they mean. And it can be a little tricky. But that's the idea. 9 double factorial, it skips over every other term. So instead of 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9, you just have 1 times 3 times 5 times 7 times 9. Odd double factorials are kind of nice. Even double factorials are even nicer. Let's look at another problem. Yeah, so 23 has an even double factorial. Let's try that one. So here they've given it to us in sigma notation. That is sigma n from 1. Numerator is 2 times 4 times 6, all the way out to 2n divided by n factorial. And just like if they gave it to us in the written out form, we should write it in sigma form. I think it's nice to write out the first few terms. The description of the numerator here, that is kind of similar to the description of the denominator we used in the previous problem. This is the product of the first n even numbers. So the very first term here is 2 over 1 factorial, then 2 times 4 over 2 factorial, then 2 times 4 times 6 over 3 factorial, and so on. That's what this numerator is describing. And again, because factorial like products and factorials, we would use the ratio test. If you want to write this as a double factorial, you can. It's 2n double factorial, but you don't have to. I wouldn't, honestly. But if you like that more, you can. That's fine. Ratio test, we're going to let L be the limit as n goes to infinity, absolute value an plus 1 over an, which for this series is the limit as n goes to infinity. And now here's where we want to be careful. An plus 1 has denominator n plus 1 factorial, and numerator 2 times 4 times 6 out 2. You could say 2 times parentheses n plus 1, just write the last term, but I think it's nice again to write the second to last term also. So the second to last term is 2n, and then you have 2 times parentheses n plus 1. So this is a sub n plus 1. And to divide by an, I'll just multiply by its reciprocal. That's n factorial over 2 times 4 times 6 out to 2n, like this. And I'll come down here. This is equal to limit n to infinity, grouping similar terms together. I'll put the n factorial over n plus 1 factorial here. And my even product, 2 times 4 times 6 out to 2n. And then the next term, 2 times parentheses n plus 1 is 2n plus 2. Downstairs we have 2 times 4 times 6 just out to 2n. A lot of terms cancel from that even product. Everything up to the 2n. And n factorial over n plus 1 factorial. We can write it out. It's n times n minus 1 times n minus 2 down to 3 times 2 times 1. Eventually, you'll get comfy enough with these just to say that it's 1 over n plus 1, and that's okay too. And then over here, we have just 2n plus 2. And here's upstairs. All of the terms from the n factorial cancel. This is why the ratio test is so nice with factorials and factorial-like products. And we get lim n to infinity 2n plus 2 over n plus 1. And I'm ditching the absolute values here because everything was positive from the start. Honestly, I could have said fuck absolute values after this step because there's no negative terms anywhere here. And very similar to the last problem, this limit is obviously 2, right? You can renormalize or use the L'Hopital's rule, whatever you want. I would say since L equals 2, which is bigger than 1, the series S diverges by the ratio test. Not too bad, right? Questions on this one? Okay. I do want to move to some 11.7 problems. So let's do that. Let me see how I'm doing on time here. Okay. All right. Let's look at some stuff that's not super obvious here. How about number 14? The reason for me choosing this particular problem, number 14 here, which is sigma sine 2n over 1 plus 2 to the n, is that your first thought, well, it might be right kind of morally, won't work. So what's our first thought when we see this series? Just share with me your feelings about this thing. Think of me as your therapist. Tell me about your feelings. Anyway. Not necessarily alternating. Not necessarily. So let's write out the first few terms of the series. When n is 1, this is the sine of 2 divided by 1 plus 2 to the 1, which I'll just write as 1 plus 2. When n is 2, this is the sine of 4 divided by 1 plus 2 squared is 4. When n is 3, this is the sine of 6 divided by 1 plus 2 to the 3, which is 8, and so on. And we don't know the sine of 2 or the sine of 4 or the sine of 6. Those are actually really nasty numbers. Let's see. What let me do this. No. There's got to be a way to put signs in here, right? Sine of 2. Fuck this thing. So the comment in chat there that this is like alternating isn't quite correct, but it's close. All right, positive, negative, negative, positive, because the sine function goes from positive to negative every time you go around by pi, right? It's positive from 0 to pi, negative from pi to 2 pi, positive from 2 pi to 4 pi, negative from 4 pi to 8 pi, and so on. And because these integers are never going to hit multiples of pi, this is going to dance around between being positive and negative, but it's not going to be purely alternating. This first term is positive. The second term, the sine of 4 is negative. 4 is bigger than pi. The third term, sine of 6, 6 is between pi and 2 pi. So this is also negative. The next term, would be sine of 8. 8 is still between pi and 2 pi, right? Or no, it isn't. No, so the next term, sine of 8, would be positive. So we are going to bounce around between being positive and negative, but it's not alternating. It's not every term changes sign, right? Positive, negative, negative, positive. Sine of 10, how big is 10 compared to multiples of pi? Well, 3 pi would be around 9. So the sine of 10, the next term would be negative. So positive, negative, negative, positive, negative. It's not quite alternating. Okay. But it's also not always positive. And because the terms are not all positive, that means we can't use the integral test, we can't use the direct comparison test, and we can't use the limit comparison test. What test would you like to use with this? Again, pretending like this issue wasn't here, what would we like to use on this guy? What does it feel like? Yeah, again, beautiful. I would like to use a direct comparison. Sine of 2n, just like the sine of anything in this universe, is never larger than 1. Right? The sine of your mom is smaller than 1. The sine of a soccer ball is smaller than 1. The sine of dog shit is smaller than 1. Because the sine function, no matter what you feed it, can never spit anything out bigger than 1. So I would like to say that this series is smaller than 1 over 2 to the n. But because the terms are not always positive, you can't use direct comparison test, limit comparison test, integral test, etc. Those are all out. And it's not quite alternating. So I can't use the alternating series test. So we've got some options here. One option, you could try a ratio test, but you'd have the sine of 2n plus 2 divided by the sine of 2n as one of your pieces in there. And that limit doesn't exist. I'll tell you right now, the ratio test ain't going to do it. There's a more powerful version of the ratio test that replaces the limit with something called a lim sup. And that would work. But again, it's not nice, and there's a better way. Thinking about what Richard said in chat, that we would like to do a direct comparison, I want to ask you the question, do you think this series converges or diverges? Based on the fact that this numerator is always smaller than 1, and this denominator is larger than 2 to the n. Just morally, do we think the series converges? Do we think the series diverges? Yeah, I agree with Coburn and Richard that this series converges. Let's go a little deeper. Do you think the convergence is conditional or absolute? Think about this denominator. Think about this being no bigger than 1. Conditional or absolute? Yeah, I want to say that this convergence is absolute. The 2 to the n downstairs grows really fast, and the top is bounded. So here's what we do. The absolute value of an here is the absolute value of sine 2n over 1 plus 2 to the n, which is less than or equal to 1 over 1 plus 2 to the n, which is itself strictly less than 1 over 2 to the n. So I'm going to use a direct comparison test, but not on the original series. I'm going to use the direct comparison test on sigma absolute value of an. Which is sigma n from 1 to infinity absolute value sine 2n over 1 plus 2 to the n. Oh, this is not a p-series. When n is equal to 1, we just have the sine of 2 divided by 3. So remember, a p-series, the only p-series are series like sigma 1 divided by n to a constant power. So this is not that. But what we can say, let me call this new series T or whatever. Since I'm using a direct comparison test, since 0 is less than or equal to absolute value sine 2n over 1 plus 2 to the n is less than 1 over 2 to the n, and sigma n from 1 to infinity 1 over 2 to the n is the same as sigma n from 1 to infinity 1/2 to the n, which is a geometric series with r equal to 1/2. So absolute r is absolute 1/2 is 1/2, which is less than 1. The series sigma n from 1 to infinity 1 over 2 to the n converges. Thus, I'll come up here and label this inequality. Thus, by the direct comparison test and the inequality, no worries, and the inequality star, the series T equals sigma n from 1 to infinity absolute value sine 2n over 1 plus 2 to the n converges. I don't know, sorry, not period, comma, which means S equal sigma n from 1 to infinity sine of 2n over 1 plus 2 to the n converges absolutely. All right, and this is a place where it's very easy to get into trouble following your intuition, because our intuition is that, yeah, my series is smaller than 1 over 2 to the n. But because my series isn't all positive terms, we can't use the direct comparison test directly. We have to use the direct comparison test on the absolute value series. Then you can show that the absolute value series converges using the direct comparison test. So all of this standard work for that absolute value series. And as a consequence, the original series converges absolutely. So this is one of those places where you need to be very careful with your logic. and make sure you understand the hypotheses of your convergence tests. Because the direct comparison test, while it is in a sense the right tool here, it does not apply to the original series. And this was that note in 11.7, right? Where they said, you know, if your series doesn't have positive terms, you can't use the comparison tests. But sometimes it's wise to look at sigma absolute value of AN instead. Okay, we've got about 5 minutes left. So let me see if we can find one more good problem to play with here. Any requests? (34). 1 over n plus n cos squared n, sure. This one is not as bad as it looks. Again, not a bad idea to write out the first few terms. So this is 1 over 1 plus cos squared of 1 plus 1 over 2 plus 2 cos squared 2 plus, I don't know here, so again, a challenge here is that cosine of 1, cosine of 2, cosine of 3, those are not nice numbers. I don't know what those numbers are, and I don't expect you to know what those numbers are. Good news here shows up in several flavors. Cos squared is always positive, right? It's the square of the cosine function. Squares are always non-negative, at least. Bad news here, let's see. So try to think about this intuitively. Between n and n cos squared n, who's bigger? It's tempting to say n cos squared n is, but remember, cosine always outputs stuff that's between -1 and 1. So cos squared always outputs stuff that's between 0 and 1. So here, n times cos squared n is actually smaller than n itself, because the cosine squared is between 0 and 1. So because cosine n itself is always between -1 and 1, cos squared is between 0 and 1. And then if I multiply everywhere by n, I see that this is smaller than n. So how can I use this, which is a true statement, to understand this a little better? Is there a way, is there something I can do to the inequality we have down here now that will make my denominator show up somewhere? Notice that I've almost got my denominator in the middle. What would I need to change? How would I need to alter this middle piece in order to make it into my denominator?
Add n.
Yeah, so let's add n everywhere. then I get n is less than or equal to n plus n cos squared n is less than or equal to 2n. So my denominator is between n and 2n. Remember, you can take reciprocals in inequalities. It flips the inequality over. So 1 over n is greater than or equal to 1 over n plus n cos squared n is greater than or equal to 1 over 2n. And one of these, so this is really two inequalities in one, right? There's this statement and there's this statement. One of them is useful, one of them is not. On the one hand here, the left inequality says that my terms are smaller than 1 over n, or 1 over n is bigger than the terms of my series. That's not helpful. But this guy, this is a useful statement. I can rewrite this as 1 over 2n, right? I'm saying my guy is bigger than 1 over 2n. In other words, 1 over 2n is less than or equal to 1 over n plus n cos squared of n. And of course, as n goes from 1 to infinity, 1 over 2n is bigger than 0. So we call this inequality star. And what I'm doing here is a direct comparison. By star, the terms of my series I'll just call it S, are larger than the terms of the series sigma n from 1 to infinity 1 over 2n. What do I know about this series? What can I do with this? It's not quite a p-series, right? If it was just 1 over n, that's a p-series. But I have 1 over 2n. Can I do something with that too? It's not geometric, no. Our geometric series are like a constant raised to the nth power. I can pop the 2 out. I can pop this 1/2 out. This is 1/2 times sigma n from 1 to infinity of 1 over n, which is a multiple of a p-series, right? This is a p-series. Sigma 1 over n is a p-series with p equal to 1, which is greater than or equal, which is not strictly greater than 1. Let's just with p equal to 1, which is not strictly greater than 1. So sigma n from 1 to infinity 1 over 2n diverges. Right? Sigma 1 over 2n is 1/2 sigma 1 over n. Sigma 1 over n is a divergent p-series. So sigma 1 over 2n diverges. Thus, phi star and the direct comparison test our series S equals sigma n from 1 to infinity, 1 over n plus n cos squared n must also diverge. And that's the game. So the trick in this one is definitely coming up with the inequality. And that wasn't terribly hard to do. I guess I'll zoom out a little bit here. You can see the inequality work as well. Started with the fact that the cosine of n is always between -1 and 1. And if you take something that's between -1 and 1 and you square it, you get something between 0 and 1. It's not that -1 squared is 0, it's just that numbers between -1 and 1 when squared give numbers between 0 and 1. All the negatives become positive, but you're still smaller than 1. Then I multiplied everywhere through here by n. 0 times n is 0. Cos squared n times n is n cos squared n, and 1 times n is n. And then I added n everywhere to make the denominator of my series terms show up in the middle. You could proceed a few different ways, but the upshot is that my terms are bigger than 1 over 2n. And the series sigma 1 over 2n is definitely a divergent series. So you need to arrive at this inequality somehow. And once you have this inequality, it's just a matter of writing down the words and remembering what the series sigma 1 over 2n does, which is not bad, right? Remember, the rules for sigma are the same as the rules for an integral. Constant multiples pop out. 1 over 2n is 1/2 times 1 over n. So that 1/2 can come out. And then sigma 1 over n, you can treat it as a p-series, which it is, because p is equal to 1, which is not bigger than 1. The series must diverge. Or you could just say it's the harmonic series, which we know diverges. Either one. This is a famous series. Thus, the terms of my series are bigger than the terms of a divergent series. So by the direct comparison test, our series must diverge. Alrighty, we are over time. I got to get running because I have another class that starts soon, but this is the sort of stuff we need to be practicing. And I really want to implore you guys to be writing out all the words, practicing doing the whole thing, and most importantly, sharing your solutions with each other. Not so that you can cheat and just put the correct answers in, but to check if your logic is sound. And if somebody has the balls to come to you and say, can you please look at this with me? Show them the respect that courage demands, and take the time to really look at it with them. You'll both learn something. And this is the best way to study for this test. So I know you guys all want to do well. The best way to ensure you do well is to practice this stuff honestly, earnestly, and to share your results with each other so you can check each other's logic. I'm happy to work with you. Of course, my time is limited and there is only one of me, whereas there are many of you. So I will do my best to answer all questions as quickly as I can, but please work with each other also. The tutors can be helpful. Alejandro at the Learning Commons, if he's still there, is wonderful with this stuff. There is nobody else there I can vouch for right now. I'm sorry to say. I trust that there are some other people there. If you see Dr. Pinon, he's a very tall, very bald, very French man. I know he does some office hours at the Learning Commons, and he is generally happy to spend time talking to any student who wants to talk to him about mathematics. I can vouch for him as well. But it's on you guys to put the time in to practice, to share with myself, each other, and anybody else you trust to check your logic, to spend time reading and making sure you're understanding what you're writing. Please write in full sentences and read what you write to make sure it makes sense, because it's very easy to just put some gibberish on the page and be like, I got the right answer, so this must be a good solution. That's not always the case. That's it for me for today, guys. I'm going to let you go. I will see you on Monday. Take care.